Hello, in this video we're going to discuss a special type of function called a rational function. And in our prior videos we discussed polynomials, and polynomials were unique because they had domains that were all real numbers and they were very easy to work with consistently. We never really had any major problems, but sometimes rational functions give us some more to evaluate. Not that they're more problematic, they just give us some more to evaluate. So first of all, let us go ahead and define the term rational function. So I know that most of you are probably thinking rational, you're thinking ratio. Ratio is synonymous with a fraction, and you are correct. A rational function falls in the form of a fraction. So we're going to say that f of x is our rational function, and it's going to be equal to g of x all over h of x, where h of x cannot equal to 0. H of x cannot equal to 0 because we can never have 0 in the denominator. And this is going to have to deal with something that we've been discussing pretty consistently, and this is going to deal specifically with the domain of the function. And that domain is going to indicate the values that actually make the denominator equal to 0. We're going to exclude those values from the domain later on. So for right now, we're defining a rational function as a polynomial or a function divided by a function. So g of x is a polynomial, h of x is a polynomial. They are functions, but specifically these are more interesting. The ones that I want us to worry about is wherever we see an x or a variable in the denominator, So yes, if we have a constant in our denominators, that's not so bad. They're not actually considered, they do have rational values if they're just constants, but they're not considered rational functions. If we have an x in our denominator, a function of x in our denominator, that's when we have a rational function. So if we look at an example, of a rational function, we could say that f of x is equal to 3 all over x minus 4. 3 all over x minus 4. This is an example of a rational function because we have this constant 3 up on top, and that's okay, but notice we have this variable x in our denominator. We have that variable x in the denominator. In fact, we have x minus 4 in our denominator, and that's going to lead us to the next part, which we should always be concerned with consistently, is the domain of the function. So how do we determine the domain of a rational function? And it should be screaming to us at this point because we should recognize that x minus 4 can never equal to one value, and specifically x minus 4 can never equal to, as we stated up here, our denominator can never equal to 0. So if we add 4 on both sides, we recognize that x cannot equal to 4. So this is an example of a rational function with his domain being the set of x such that x cannot equal to 4. Or you can write this in interval notation, which I don't often like to do at this point, negative infinity to 4, and then we're going to conjoin this with 4 off to positive infinity. So we actually do have a rational function that has a domain where value of 4 has to be excluded. So that's a great example of a rational function. Let's go ahead and look at another example of a rational function. And in this example, we might be given a value of x equals to x minus 2, which is okay, all over x squared minus 9. And notice here, this is rational. We have a polynomial up on top. We have a linear polynomial up on top, this x minus 2. And then we have this x squared minus 9, which is this parabolic type. This is quadratic type function. So that x squared minus 9 in our denominator, that's also considered a rational function. And specifically here, we recognize that if we want to find the domain of this problem, we know that x squared minus 9 cannot equal to 0. Solving this, we can do it by adding 9 on both sides. But when we take the square root, be careful. Because we're going to have to add a plus or a minus value in front of that square root of 9, which is equal to 3. So here, x cannot equal to plus or minus square root of 3. X cannot equal to plus or minus square root of 3. Writing this in set notation, we're going to have the set of x such that x cannot equal to plus or minus 3, or we can write this in interval notation, very long and drawn out, from negative infinity until negative 3, union, negative 3 to positive 3, union again, 3 to infinity. Every number on that number line except positive and negative 3. we're going to learn at these values, when x equals to 3 and negative 3, we're going to have some special characteristics, and we're going to learn about something called asymptotes. And when x equals to 3 and negative 3, we're actually going to have a vertical asymptote graphically at these points. But for right now, all we have to do is identify a rational function, and specifically the domain. And eventually, these will be very clear to you. We want to make sure to identify them very rapidly, because domains are very similar to me going into a grocery store, and I walk over and I see a banana, and I recognize that it's a type of fruit. I walk over to the meat section, I look at a piece of chicken, and I know that's poultry. If I walk over to the snack food section, I see a bag of chips, I realize that's bad food for me, which I know isn't really a type of food. I'm just trying to make a little joke there. But when I walk into a grocery store, I can look at a food, I can tell you what type of food it is most of the time. Unless I go into one of those international stores where I don't recognize a lot of the foods, and then I have to do some research. But however, the same exact thing should scream to us. When we see a polynomial, we should recognize domain all real numbers. When we see a rational function like what we're working with now, we should recognize that this has a domain restriction. Let us look at one more example of a function before we cut this video. Let us say we said f of x equals to 3 plus 2x all over a value of 5. And we say, okay, so if we want to, this looks rational, we have a numerator, denominator, but let's go ahead and evaluate this domain. And we would say the domain of this function is that 5 cannot equal to 0. But we think to ourselves, does 5 ever equal to 0? And that answer is no. And the reason why 5 never equals to 0 is because 5 is just a constant. So notice in our definition specifically, we say that our denominator has to be a function of x. And notice here we don't have a function of x, we just have a constant. So this is actually an example of a polynomial, because this simplifies into 3/5 plus 2/5 x, and this is a linear function, and linear functions are types of polynomials. So sometimes they can not scream to us like we used to. However, after becoming more fluent with these types of graphs and with these types of functions, we will recognize them quite quickly, and we will not have to worry about debating what types of functions that we have.